Now, it's time for the session you've all been eagerly awaiting. It is with great honor and humble pride that I stand before you today to introduce our distinguished guest speaker in this evening. Ladies and gentlemen, he earned his BSc in Mathematics from the University of Colombo, went on to obtain an MSc in Mathematics from the New Mexico Institute of Mining and Technology, an MSc in Mathematical Sciences from Clemson University, and MSc in Computer Science from the College of William and Mary, USA, and later went on to obtain his PhD in Statistics from Old Dominion University, USA. As a member of the American Statistical Association and the New Zealand Statistical Association, he remains at the forefront of the latest development in the field, contributing to its growth and evolution. Ladies and gentlemen, let me invite Dr. Sathish Indika on stage to deliver his lecture.
Hello, good evening everybody. Can everybody hear me? Okay. So thank you so much for coming this evening to this lecture. I want to thank Dr. Singh and other professors in the math department who organized this lecture. And I want to thank the Mathematics Society for organizing this lecture. So my name is Sathish Indika. So today I'm going to talk about exact expressions for trig functions. Joint research work with Dr. Leamis at the College of William and Mary, Department of Mathematics. So this paper has already been published at the College Mathematics Journal, CMJ. It is a journal of one of the journals, I would say, of the Mathematical Association of America, MAA. So this is the information about the journal, and this paper is now published in CMJ volume 55, issue 1, 2024. Right here, this is the link. So this is the, the first page of the paper. Okay, so I'm going to discuss our work. But before that, I am going to very, very briefly talk about history of trigonometry. I will focus on the Greek period and the Indian mathematics, ancient Indian mathematics. Okay? Then I will talk about the paper. Okay, so what is trigonometry? Trigonometry, this is derived from these two Greek words. This Greek word, trigonom, means measure. And this Greek word, metron, means, trigonom means triangle, metron means measure. So, trigonometry. So, trigonometry is a field of mathematics, we all know, right? So, this is one introduction about trigonometry. So it's understanding and developing the relationships between angles and ratios of lengths of planar figures and three-dimensional figures. This is just one explanation. I mean, there are many definitions or explanations about this field of trigonometry. Yes, 1 minute. Okay. So I'm going to go to the next slide. So, origins of trigonometry. So I'm going to talk about very, very briefly. So, you know about Sumerian, civilization, right? Sumerian astronomers, they studied the angle measure. They considered this 360-degree concept that we all talk about today also, right? And like Sumerians, Babylonians also studied ratios of sides of similar triangles. We know similar triangles from, grade 9, 10 from onwards, right? Okay, so I'm going to briefly talk about the Greek period, Hellenistic period, Hipparchus. So this is the, Greek word, Hipparchos. I'm not sure I'm pronouncing this correctly. From Nicaea. Nicaea is an ancient city in the Anatolian region of Greece. So he is considered the father of trigonometry, Hipparchus. He gave, he was the person who gave the tables of chords, similar to the sine tables that we have. Then Ptolemy. Ptolemy is also a great Greco-Egyptian mathematician, astronomer, astrologer. So he constructed detailed trigonometric tables. So I'm going to talk about the Indian civilization, Indian mathematics little bit. So everybody knows, I'm sure, Indian civilization dates back to at least 2000 BC, 2000 BC. So approximately, from 800 BC to 200 AD, we see a development of a primitive kind of mathematics. So you are talking about how many years? 800 BC to 200 AD. So during that period, so there was some kind of primitive mathematics developed in ancient India. So around 300 BC, they had a number system called Brahmin symbols. So as far as our talk is concerned, what I want to say is early and very significant developments of trigonometry happened in India. Okay, so I'm going to talk briefly about some Indian mathematicians, So Aryabhatta, he's a leading Indian mathematician, astronomer. India's first satellite was named after him. He made developments of what are called Siddhantas. And his major academic work, Aryabhatiya and Arya Siddhanta, two of his major academic works. Then we have Bhaskara. Bhaskara is also a mathematician and an astronomer. So he was the first mathematician to write numbers in Hindu-Arabic decimal system. He used a circle to represent 0. Now we know, now it's not, everybody knows we put this 0, right? But back then, think about that time, right? So ISRO. ISRO is the Indian Space Research Organization. They are June 1979, they put out a satellite named after Bhaskara 1. Okay, so do you have any questions so far? Okay, so moving along then. Okay, Brahmagupta during this period. Brahmagupta. He was also a mathematician and astronomer. He gave rules for computing with 0. What do you mean by computing with 0? Now we know every number multiplied by 0 is equal to 0, right? Right? Anything divided by 0 is not defined, right? So he gave some rules about computing with zero. And he identified gravity as an attractive force. He gave the term Gurutvaakarshanam. So the Sinhalese word is Gurutvakarshana, right? Right? Gurutvaakarshanam. Okay, so Bhaskara II during this period, 1114 AD to 1185 AD. Bhaskara II is also called Bhaskara Acharya. He is considered the greatest mathematician in medieval India. Some of his main academic work is called Siddhanta Shiromani. Another academic work. So these are all mathematical, physics texts. Karana Kautula. Okay, so Bhaskara II, Bhaskara Acharya, he developed many trigonometric trig formulas, results. Some of the results he developed. Of course, during that time, these formulas were not written like this. I mean, they used little bit differently they wrote. But nowadays we use these formulas like this, right? Correct? And he computed sine of 18 at the exact value, square root of 5 minus 1 over 4, sine of 36 degrees, square root of 5 minus square root of 5 over 8. Then I will talk about Madhava. Madhava of the place he lived called Sangama Grama. He was also called Madhavan. He was the founder of Kerala School of Astronomy and Mathematics. You know the modern state of Kerala in southern India. And he was born in this place called Sangama Grama in the kingdom of Cochin during that time. Now this is the modern state of Kerala, right, in India. He made leading contributions to trigonometry, infinite series, calculus, algebra, geometry. So this was done around 14th, 15th century, right? So 300, 400 years before the Europeans were talking about these concepts. So you have to understand that they were talking about these 300, 400 years before. So some of the results of Madhava, I have one or two, but he made so much contribution to this field, Madhava. Okay, so I'm going to now start talking about our paper. Do you have any questions, comments, or do you want to add anything? There are so many other Indian mathematicians called Varahamira, Leelavati, right? So I forgot some of other names, but okay, so I'm going to talk about, the modern period. So many authors considered finding exact values for trigonometric functions of certain angles. Dr. Brady, I know him actually. He's at the Christopher Newport University in Newport News, Virginia. So he had a paper back in 2002. He considered an approach based on geometry to derive the values of the sine and cosine for multiples of 18 degrees. So this was Dr. Brady's paper. It was also published in the College Mathematics Journal back in 2002. Then Dr. Kowalski, back in 2016, he obtained the value of sine 1 sine of 1 degrees, sine 1. We know sine, what is the value of sine 30? What is the value of sine 30? I cannot hear anything. Huh? Point 5. Yeah, 1 over 2.5. So he obtained the value of sine of 1 through different mathematical techniques. He used geometrical methods, algebraic techniques, techniques in complex analysis. Okay, so moving along. So now, in our work, we considered the derivation of exact expressions for the cosine angle between 0 to pi over 2. Now, when you have the value cosine alpha, right? When you have cosine alpha, you can find sine alpha, tan alpha easily, right? Once you have one value, you can find the others, right? Now, everybody is familiar with the half angle formula, right? Half angle formula, normally we write plus or minus, right? But in the first quadrant, it is just plus, right? I mean, cosine alpha over 2 is equal to square root of 1 plus cosine alpha over 2. During the triple angle formula. Now, this formula, we can rewrite this formula like this, right? This is the modified triple angle formula. Okay? Okay. So now our goal was to develop 1/3 angle formula. 1/3, right? 1/3 alpha over 3. 1/3. Okay, so let us take lambda equal to cosine alpha and y is equal to cosine alpha over 3. So now alpha is an angle in this interval 0 to pi over 2. Okay? So now let us use these definitions and substitute to this modified triple angle formula. Lambda is equal to cosine alpha, right? Y is equal to cosine alpha over 3, right? This will become 4 times y to the power 3, right? Correct? So lambda is equal to 4 times y to the power 3 minus 3 times y, right? Correct? So earlier I had lambda is equal to 4 times y to the power 3 minus 3 times y, right? So that equation can be written like this. What is this equation? This is a third degree polynomial equation. Degree of this polynomial is 3. Highest power in the variable y, right? Third degree polynomial equation. Okay. Any questions, any comments? Okay, moving along. Okay, so this cubic polynomial has no quadratic term. There's no quadratic term, right? I mean, if you write a polynomial of degree 3, let me write something on the board. So, polynomial of degree 3, right? So, let me write that. F of y is equal to a3 times y to the power 3 plus a2 times y to the power 2 plus a1 times y plus a0, right? Right? This is a polynomial of degree 3, right? Right? The leading coefficient is a3, degree is 3, right? Now, this polynomial has no, the second quadratic term is missing. That's what I'm telling, right? So, that has this form y to the power 3 plus py plus q. So, this is called the depressed, it's missing something, right? Depressed cubic equation. Depressed cubic equation. So, this depressed cubic equation, so if you have something like y to the power 3 plus py plus q equal to 0, this cubic equation, right? How do you solve this cubic equation? There are many methods, right, nowadays, but you can solve this also using Cardano's formula. Right? Now let me talk something about the great man Cardano. Okay? So Cardano, Girolamo Cardano, 1501 to 1576. His Cardano, whose interests and proficiencies range through of mathematician, physician, biologist, physicist, chemist, astrologer, astronomer, philosopher, writer, and gambler. Things also. So we can solve this equation using Cardano's method. Okay, so moving along. Okay, so we had this equation on y to the power minus 3 over 4 times y. We have a figure 1, like not next slide, like 2 slides back, but I will go to that figure very soon. We have the graph of f of y, this polynomial function for lambda is equal to 1 over 2 on this domain. Now, we have the endpoints, local min, local max, the vertical intercept of the graph, right? And the 3 roots along the horizontal axis. Okay, so let me go to the graph. Okay, this is the graph. Okay, so f of minus 1 is equal to this value. Okay? F of 1 is equal to 1 minus lambda over 4. I mean, you can easily find those, right? I mean, what is the function? The function is equal to f of y is equal to y to the power 3 minus 3 over 4y minus lambda over 4 on this domain, negative 1 to positive 1. So f of 1, you can easily find that, right? Substitute 1 for y, right? Okay. So that is the graph of the function, the depressed polynomial. So you have at this function, so it's throughout the domain, it's increasing to a mean, right? And then decreases. This is the vertical intercept, and decreases, and that increases. Okay, so what are these points? This one, and this one. What are those points? This one, and this one. Those are the points. If I make this equation equal to 0, those are the intercepts, right? Correct? So, if you make f of y is equal to 0, that means y to the power 3 minus 3 over 4 times y minus lambda over 4 equal to 0. So those intersection points, right? Or what you call the solutions of this equation, right? Solutions of this equation right here are this one, and this one, right? Correct? So let me go back a little bit. So, okay, so I said generic labels were placed on the vertical axis. Over 3. The positive real root is cosine alpha over 3. Okay? So now you see that we are combining polynomials with trigonometry, right? Okay, so inflection point. So now you can easily find the inflection point. Take the first derivative, take the second derivative, right, equate to 0, you can find the inflection point, right, from calculus, right, basic calculus 1, right. So the inflection point is this ordered pair. Y coordinate is 0, f of y is, f of 0 is negative lambda over 4. So let me go to the graph. This is the inflection point right here. Okay, so slope of the tangent line at the inflection point is always negative 3 over 4. Slope of the tangent line. So if you draw a tangent line at this tangent line, right? If you draw a tangent line at, right here, slope of that tangent line is always is always negative 3 over 4. Negative 3 over 4, whatever the value of lambda, regardless of the value of lambda. So moving along. So we made very good points about the roots, right? Okay. Now, what do you think about if you change the value of lambda, what will happen to this graph? It will vertically only, it will be only vertical move, right? It will be only going up or down. When you change lambda, it will go up or down. It will never go like this. There will not be any horizontal move, right? There will only be vertical when you change lambda. So that means, you know, the fact that there will be two negative solutions and one positive solution will not change. Right? Because you are not doing any horizontal shifting. Okay? Okay, so now let's look at an example. So, we will take alpha is equal to pi over 3 radians. That's 60 degrees, right? Pi over 3. So, lambda is equal to 1 over 2. Okay, so what is the depressed cubic equation then? When I put lambda is equal to 1 over 2 for here, you get this equation, right? So, P is equal to negative 3 over 4, Q is equal to negative 1 over 8. Okay, so this is the Cardano's formula right here. So, if you use Cardano's formula, you will get a value for cosine pi over 9, alpha over 3. So, we take alpha is equal to pi over 3, we get y is equal to cosine alpha over 3, right? So, alpha over 3 will be pi over 9. So, from this formula, with P is equal to negative 3 over 4, Q is equal to negative 1 over 8, we get an exact value for cosine pi over 9, right here. Okay, so this website has some trigonometric exact values for dozens of other angles. So the trigonometric function values are expressed as radicals if you go to this website in Wikipedia. Okay, so moving along. Okay, so now I am going to talk about the general result. Okay, so a more general solution of the depressed cubic equation, that's a depressed cubic equation, is this equation. So we have this result, the three results given in theorem 1. So those three results will correspond to the three roots that I mentioned. 1, 2, 3, 3 roots. Okay. So let me talk about theorem 1. So that is the only theorem in the paper actually. So the cubic function, cubic polynomial in y, that one right here. Third degree polynomial, depressed polynomial. So what is lambda? Lambda is equal to cosine alpha. Alpha is the given prescribed angle. Alpha is between 0 to pi over 2. So alpha is an angle in the first quadrant. Okay. So then we have y is equal to cosine alpha over 3, y is equal to negative cosine pi minus alpha over 3, and y is equal to negative cosine pi plus alpha over 3 are roots of this f of y. Okay. Then we have results. What is cosine alpha over 3 equal to? What is cosine pi minus alpha over 3 equal to? What is cosine pi plus alpha over 3 equal to? In the next page. So cosine alpha over 3 is equal to this expression, 1 over 2 times, so open this big parenthesis, cube root of lambda plus I times, I is square root of negative 1, right? Square root of 1 minus lambda squared plus cube root of lambda minus I times square root of 1 minus lambda squared. Now, if you look at this complex number over here, inside the square root, lambda plus I times square root of lambda, square root of 1 minus lambda squared, and this one, lambda minus. So they are what are called complex conjugates, right? A plus IB, A minus IB, right? So you have cube roots of complex conjugates, right? Here, okay? Then cosine of pi minus alpha over 3 is equal to this expression. I'm going to tell you what is omega 1 and omega 2 in a minute. So this expression, and cosine pi plus alpha over 3 is equal to this expression. So it's omega 1 times inside this, omega 1 times that, this one, this cube root. Omega 2 times this cube root. Then cosine pi plus alpha over 3, you have, you interchange. Instead of omega 1, we have omega 2 here. Omega 2 is replaced by omega 1. Okay? Omega 1 and omega 2 are cube roots of 1. What do you mean by that? I mean, if you solve this equation, omega 3 is equal to 1, right? Cube root of 1, right? You will get 3 solutions. One is a real solution, the other 2 are complex solutions. These are those 2 solutions, omega 1 and omega 2. Okay? So we have the theorem now in the paper. Okay, so I'm almost done. Within 5-10 minutes I'm done. Okay, so the next part in the paper. So what is the next part in the paper? The iterative application of the formulas. What are the formulas? Now we can use this 1/3 angle formula, right? I have an angle alpha, I want to find cosine alpha over 3, 1/3 formula. So you can combine the 1/3 with the half angle formula, or the double angle formula, or the triple angle formula, iteratively, right? And you can generate an exact expression for cosine of 2 to the power I over 3 to the power j times alpha, or cosine of 3 to the power k over 2 to the power l times alpha. Now, why do we have this factor 2 over 3 or 3 over 2. So you can, depending on this ij or kl, you apply in the triple angle or double angle, right? Or alpha over 3, right? Okay, so for any angle alpha in the first quadrant, for integers I, j, k and l. Now, we have to be very careful that this factor 2 to the power I over 3 to the power j must be less than 1, right? Or 3 to the power k over 2 to the power l less than 1. Okay, so let's consider a situation. So let's take I is equal to 1, j is equal to 1, alpha is equal to pi over 6. So I is equal to 1, j is equal to 1, I is equal to 1, j is equal to 1, alpha is equal to pi over 6, right? Right? So 2 over 3 times pi over 6, right? That's pi over 9, right? 2 over 3 times pi over 6, pi over 9, right? So you want to get cosine pi over 9, right? So how do you get cosine pi over 9 iteratively? First, apply the 1/3 formula. So we are starting with pi over 6, right? So from 1/3 formula we get the value of cosine pi over 18, right? So lambda is equal to cosine alpha cosine pi over 6. So from theorem 1 you get cosine alpha over 3, so pi over 18. So basically you just apply sorry, I'm going forward. You just apply this formula, right? This one, top one. So you get cosine pi over 18, right? Now, I want to get cosine pi over 9, right? So next step, I will apply the double angle formula. So cosine theta is equal to 2 times cosine squared, right? Double angle formula, right? So cosine pi over 9 is equal to 2 times cosine squared pi over 18 minus 1. I have the value of cosine pi over 18, right? So I can get the value of cosine pi over 9. Exact expression. So in that example we applied 2 times. I is equal to 1, j is equal to 1. First 1/3 angle formula and then the double angle formula, right? So you can create many examples like that, right? But you need to make sure that this ratio must be less than 1, or this ratio, if you consider ij, the ratio must be less than 1. If you consider kl, ratio must be less than 1. So this is the exact value for cosine pi over 9. So you can create many examples for classroom exercises, or you can write computer programs, computer code using computer algebra system like symbolic programming languages like Maple, Mathematica, right? Using Maple or Mathematica, you can write a computer program to automate this procedure. So somebody gives alpha, I or j, and you can create an algorithm to find the values that you need, right? right? The previous example, we fixed I is equal to 1, j is equal to 1. Right. We want to get the value of cosine of pi over 9. Okay, so I'm going to summarize now. So, summarize what we have done in the paper, basically. So, normally, polynomial equation solving, right, and trigonometry, those two topics are not taught at the same time. Normally, they are taught everywhere in the world as separate modules, or even in separate classes, right? You know, when you take pre-calculus, you study polynomial equations, right? Pre-calculus 1. When you study pre-calculus 2, you take trigonometry, right? Now, this concept of this 1/3 angle formula derivation give us the chance or the opportunity to combine or tie these two topics together. So that's what we did in the first major part of the paper, and we had a theorem also. Then we had that algorithm for finding the cosine of 1/3 angle. That was based on Cardano's method, formula. So finally we combine this algorithm with half angle formula, double or triple, to get exact expressions for trigonometric functions. So written in terms of radicals for angles, for any number of angles between 0 and pi over 2. So that's the references. So I think we made it before 1 hour, right? Correct. So I know it's getting late, and it's 6:55 now, right? PM, right? So do you have any questions, comments, things like that?
Thank you very much, Dr. Indika, for the interesting lecture and those pearls of wisdom. It was a great having you here as a speaker for today. And I kindly request you to remain on the stage to receive your token of appreciation, and to present the token. I invite Dr. Pasanedru Singha, Senior Lecturer at the Department of Mathematics, on the stage. Thank you, Dr. Indika. It has been a privilege having you here today, and I am certain that your insights did enlighten and inspire us all this evening. Moving on, I'd like to call upon the Secretary of the Mathematics Society, Ms. Diniti Lianagay, to deliver the vote of thanks.
Ladies and gentlemen, as we bring this remarkable event to a close, I stand before you with a heart full of gratitude on behalf of the Mathematics Society of the University of Moratuwa. I extend a warm thank you to each one of you for being a part of this enlightening session. Today has been a truly remarkable experience, as we had the privilege of hosting the esteemed Dr. S.H. Sathish Indika, whose profound insights and expertise added immense value to our mathematical voyage. First and foremost, our deepest appreciation goes to our distinguished guest, Dr. Sathish indika. Your insightful talk, rich with knowledge and passion, has enlightened and inspired us all. Your commitment to the field of mathematics is truly commendable, and we are grateful for the intellectual feast you provided. We express our deepest appreciation for your time, expertise, and the passion you bring to the world of mathematics. Your presence with us here today has elevated our event to new heights. A special thank you to the audience, whose presence and engagement added vibrancy to our gathering. Your enthusiasm and participation made this event truly memorable. Once again, thank you all for your presence, contributions, and enthusiasm. Have a wonderful night.